Alright everyone. So in this video we're going to be looking at one of our first applications using actual calculus theory. This covers something called rates of change. This is going to be kind of your introduction to quote-unquote word problems in calculus. These are not as difficult, believe it or not. We've actually covered a lot of this content already. We're just going to reorganize it now so that we can make some sense of it. We can kind of do some stuff with it. I want to start off with this do now problem. I am going to ask you guys to turn in this first problem here, this do now problem. We're going to do it together here in the video. I'm going to ask you guys to do it along with me, and we are going, and then you'll turn it in as part of a warm-up grade the next time we have class. So let's run through the context of the problem here. We have Charlotte throws the ball into the air, and Rachel figures out the equation. This is height given time is going to be equal to negative 3t squared plus 12t models the path of the ball, where t is time in seconds and h is the height of the ball in feet. And we're going to graph this equation and use the graph to answer the following question. So with these questions, I really want you guys to, it's going to be important that you start graphing these things. So we'll talk about using the graphing calculators again, and other resources that we have available to us, like Desmos or GeoGebra and stuff for graphing these. I am going to use GeoGebra for these. I just like the flexibility that GeoGebra offers me. So the first thing I'm going to do is I'm going to graph this function. So we're going to graph h of t is equal to negative 3t squared plus 12t. Alright, so you guys can stop the video and graph that. When you are done graphing it, you should end up with a graph that looks like this. There's actually a lot of information that you guys get from this particular graph. Let's see if they give us any units in this thing here. They really don't. We're gonna, okay, for our purposes, because I'm going to say it this way, let's assume height is going to be, oh, here it is. It's time is in seconds. Time is in seconds, and height is in feet. Okay. So we actually get a really interesting picture here when we look at the graph of this particular function. What we will notice here is that for height starts at 0. Height is going to be our y variable. Time is our x variable. So we throw a ball into the air. It starts at 0 height, and it reaches a maximum height of 12 feet, and then it returns to Earth by the forces of gravity, and the whole trip takes approximately 4 seconds. So there's actually a lot of information that we accumulate from this. We don't really pay attention to anything that happens below the x-axis because these are all negative heights. Negative heights don't make sense unless you go straight through the floor or something along those lines. And negative time doesn't make any sense because, well, that's science fiction. So we have this chunk of a parabola that we're paying attention to. We're going to take a look at all this information that we have here now. So let's look at, we have our graph now. Let's ask some questions here. At what time does the ball hit the ground? So if we just look at here, we have it starts, so for our purposes, it's going to start at a height of 0. It goes up, it reaches an apex, and then it comes back and hits the ground. By our graph here, it happens at after approximately 4 seconds, just from reading the graph. Okay. Number B, when does the ball reach its maximum height? The maximum height is the apex of our graph, which occurs here at after 2 seconds. And so at 2 seconds, it reaches a maximum height of 12 feet. Okay. Then here for C, what is the maximum height? Oh, we already did that one. The maximum height of the ball is 12 seconds. So we got all of that information from the graph. There actually is another way to do it using some of our calculus tricks. So I'm going to switch screens here really quick, and we'll take a look at here. So at what time does the ball hit the ground? So the ball hits the ground at 0. You'll notice this sure does look like a parabola. So if I switch over here to this screen and I turn on my camera, there we go. Alright, so we have h of t is equal to negative 3t squared plus 12t. Well, this is just a quadratic. I mean, we're just looking at a parabola. So we want to know when the height is equal to 0. So go ahead and solve this. This is what I actually want you to do. I already gave you guys the answers earlier in the video. I actually want you guys to do the algebra and the calculus at this point. So I want to know, when is the height equal to 0? So this is the function we're working with. We'll set it equal to 0. I have negative 3t squared plus 12t. And you guys can skip ahead or speed it up or whatever you need to if you guys understand how to do this part. You should know how to do this. This is some Algebra 2 content at this point. So we have 3t squared is going to be equal to 12t. You can divide the t's out. Actually, let's divide the 3's out first. We're going to get t squared is going to be equal to 4t. We can divide out a t, and we get that t is equal to 4, which was the answer that we got from our graph. Okay, so that takes care of the first one. So that takes care of A. Okay. All right, let's take a look at B now. Okay. B is when does the ball reach its maximum height? So if we look at our graph here, the maximum height occurs at 2 seconds, and it occurs here at the apex. Now, you need to think about instantaneous rate of change here. That's a big part of what this whole section is going to be about. Is about the differences between, or applications of them rather, of average rate of change and instantaneous rate of change. Okay. Instantaneous rate of change is what we call a tangent line. So it's the example that I did in class. If I'm spinning something and I let go of it at a certain point, where does it shoot off to, sort of thing. So if I threw a ball into the air, it's climbing, gravity's starting to slow down, it reaches the apex, and let's say that the laws of physics just broke down at this point. Where would the ball keep going? We no longer have gravity, we no longer have any other forces applying to it. It tapers off here, so it reaches, if you guys are watching the video, or watching my little, the picture in the bottom of me, you're going to see that it climbs, and if it stops right, and if all of physics ends at that point, it keeps going straight across. So it's going to create a horizontal tangent line at that point. Okay, so we have some tricks here. This is really what this whole section is going to be about, is you guys learning to use the derivative to find these things. So if I plug in here, this is going to be y is equal to 12. Okay, that gives me this line here, right here at the peak, at the apex. What we should be able to do is we should be able to take the derivative of this function. Should be able to take the derivative of this function that we have here. We should be able to set it equal to 0 because the derivative is a slope predictor. We should be able to set it equal to 0, and the value that it occurs at should match the x value that we get here when we graphed it. So at x equals 2, we would expect to have a tangent line that has a slope equal to 0. So we're going to take the derivative of this thing. So that'll give us, scoot this over so get some stuff out of the way. All right, so I'm going to find h prime of t. Okay, sorry here. All right, so using the power rule, take your derivatives. So we're going to have negative 6t plus 12. Okay, make sure I did my math correctly. Everything looks good here. All right, so we want to know when the slope predictor is equal to 0. So we set this equal to 0. I'll get negative 6t plus 12. Move the 6t over. We get 12. Divide by 6, and we will get 2. So at time of 2 seconds, we should have a tangent line slope that is equal to 0, and if we go back to our graph, that is the x value that correlates with our apex. So that answers B. Okay. All right, and that brings us to our last part here, which is C for our do now. Okay, what is the maximum height of the ball? Okay, we know that our apex happens at, there we go, okay. We know that our apex happens at t equals 2, so now this just becomes a question of what is h of 2, and it should be equal to 12 from our graph. So I'm going to plug in 2 into my original function here, and we'll see what we end up with. So we get negative 3 times 2 squared plus 12 times 2, which will be equal to negative 3 times 4 plus 24. So I get negative 12 plus 24 gives me a maximum height of 12, which was the answer we got, that we got from our graph. There we go. Okay, so that takes care of the do now. I'm going to ask you guys to turn this in at the start of next class. I'll give you guys a grade for completing it. Let's go back to our handout here. Okay, so rates of change, the average rate of change. We'll see what you guys remember from when we were first starting to work with tangent lines. Remember, we have two fundamental problems in calculus. The first one is how do we find the tangent line of a curved line? Okay, and the other part of that is how do we find the area under a curve, which we will do when we start doing integration. So, when we were starting off with all of our tangent line stuff, the average rate of change, you may remember, was the slope of the secant line. And the instantaneous rate of change was the slope of the tangent line. Okay, So this is going to make a difference later because we will ask, the questions will be worded in such a way that we will be asked to find either what is the velocity at this specific time, that'll be instantaneous rate of change, or we'll be asked to find what was the velocity of such and such object during this point in its flight path. So from basically 1 second until crash landing, what was the speed of the ball or what was the speed of the plane, sort of thing. And we can measure that because we can find both of those points and calculate the values and find the average rate of change. So instant rate of change will be the snapshot moment. It's the speed that something is going at a given point in time. An average rate of change is the average velocity over a period of time. Okay, all right, let me get rid of these so I don't print them next year when I do this. Okay. All right, so we'll go to the next page now. Position. So, construct from height versus multiply the equation. Okay. In general, the position equation is going to be whatever the original function you're given to is going to be your position equation or your position function. So, if we go back to our first example, this do now problem, our position function is going to be this height function. And there's other functions that show up here. This is where we're starting to make a transition from mathematics of the sense of algebra and manipulating numbers and variables and stuff that we do in Algebra 2 and pre-calculus to starting to tie it in with physics. To be very honest with you, the entire study of physics requires calculus for you to really understand what's going on. But that's getting a little bit beyond what we want to talk about here. So, anyways, let's go back here. So we have our position formula here. So the position equation, SC gives position of an object relative to time. Common use for rates of change or to describe the motion of an object. That's pretty straightforward. So a ball's position that is dropped from a height of 100 feet is modeled by the equation blah. You're going to start seeing some numbers a lot for these equations. This will come back when we start doing related rates, which will be the next big application that we do for our calculus concepts. You're going to start noticing some numbers that show up a lot. You're going to start seeing 16 a lot and 32, and sometimes you'll see 8. And we get those specific numbers and coefficients because the acceleration of gravity is 32 feet per second per second. So you'll notice if you take the derivative of this, you'll end up with negative 32 feet. That comes from the velocity formula, which is the velocity or the acceleration of gravity constant. So that's where all of that comes together. So everything you guys did in your physics class, or you did in your guys' introductory, your conceptual physics class back as freshmen and stuff, it all comes back to this. This is where it all came from. Okay. All right, so we'll go to the next page now. Let's look at velocity. So the average velocity of an object is given by this. This part I'm not so concerned about. This is all true. The part I really want you guys to take away from this is that the average velocity of an object is just the slope of the secant line. And we know how to find a secant line. That's your y equals, oops, go back. Okay, that slope of the secant line is just your y equals mx plus b stuff that we did from Algebra 2. It's stuff you guys should be able to do as long as you have some way of identifying 2 points, you'll be able to find the equation of the line running through those 2 points, and the slope of that line will be your average velocity. Okay. The velocity or the instantaneous velocity. So when you guys are doing the homework assignment, when we're doing examples in class, and when I ask you questions concerning these, you guys really want to pay attention to language, and you want to pay attention to context. So context is a bigger thing in statistics, but in calculus and physics applications and stuff, really understand and read and understand everything that we're doing, because it does have an impact on what it is you're trying to find. A secant line tells us of something very, very different from what instantaneous velocity or what actual velocity is. So just remember, average velocity is the slope of the secant line, and velocity or instantaneous velocity is the slope of the tangent line. Okay, we find the tangent line by taking the derivative. Okay, all right, so let's go to our next slide. We'll do an example. So a ball's position that is dropped from a height of 100 feet is modeled by this equation. What is the average velocity over the time interval 1 second to 2 seconds? So this is average velocity, so this is going to be it's average velocity. So what we're looking for here is going to be the slope of the it's been a long day. The average velocity, so this is going to be the slope of the secant line, okay, for number 1 here. But in order to do that, we need to find the position or the y values that go with each of these. So let me write this down really quick. Grab my sheet of paper really quick here, and then I'm going to switch the screen over. So we've got s of t is equal to negative 16 t squared plus 100 over the time interval of 1 to 2. So let's do 1 together here. What equation represents the velocity at any time t? We'll come back to those in a minute here. So let's deal with the first part here. Let me switch the screen here so you guys can see what I'm writing. Okay. So here's the function we're working with. We're looking at the time interval over 1, 2. Let's turn these into actual points. Okay, so in order to do this, we need the actual points. So we're going to plug these values in here. We need to know what s of 1 is, and we need to know what s of 2 is. So s of 1 is going to be negative 16 plus 100. S of 2 here is going to be negative 16 times 4 plus 100. This is where a calculator comes in handy. Okay. Grab a calculator. You guys can speed this along if you guys need to. I'm just going to do the quick calculations here. So we have negative 16 plus 100 is equal to 84. That's right, your math teacher cannot do basic mental math. So negative 16 times 4 plus 100 is 36. So that gives us a couple of points to work with here. So at 1 second, we have a height or a position of 84 something and others. And at 2 seconds, we have a height or position of 36 units of measurement. They actually give us that by some height of, okay, so it's going to be, it looks like it's 100 feet, and we'll assume seconds. Okay. All right, cool. You have 2 points here. We are looking for average velocity. So average velocity is just the slope of the secant line. Okay, so all we're going to do is we're just doing y is equal to mx plus b. Okay, this is where all of your Algebra 2 skills come in here. You have 2 points. You guys know what the slope formula is. I'll let you guys do all the calculations and figure out what b is here. I'm not actually going to do this part here. I'll let you guys do that on your own. If you have questions about the answer that you get here, ask me about it tomorrow in class, and we can go over the problem in more detail. I don't want to waste a ton of time in this video going over some of the nitty-gritty details. So let's go back to number 2 here. What equation represents the velocity at any time t? So if we go back 1 page here, velocity is instantaneous velocity, which is the slope of the tangent line. So what we're looking for here is the derivative of this function. So we'll go back here. Let's just find the derivative of this. So we are looking for s prime of t. So we're going to get negative 32t, and then the derivative of a constant is always 100. So that is our instantaneous velocity formula for any given time t for this particular scenario. Okay. All right, and 3, what is the velocity of the ball at t is equal to 2? So in order to do that, remember velocity is given by the tangent line. So what we need is we need our slope predictor, and then we need to know, and then we need to plug that value in here. So we're going to plug this value in for t. So we're just looking for s prime of 2, which will be negative 32 times 2, which is equal to negative 64. Okay, so what this tells us, we don't quite have a full story as I recall here. So a ball's position is dropped from a height of 100 feet. What this is saying is that from 100 feet, hold on a second here, what is this telling us? What is the velocity? Oh, so this is just saying that the ball is dropping due to the acceleration of gravity. It is dropping at a rate at 2 seconds of negative 64 feet per second. You guys should have covered this in your physics class, but the acceleration of gravity is not constant until you have reached something called terminal velocity. So if I have a pen right here. If I drop this pen, it's actually accelerating. So it starts at 0, it picks up speed, it's continuing to pick up speed until it reaches terminal velocity. And terminal velocity for a different object is based upon wind resistance and the mass of the object and a whole bunch of other factors and stuff. It's actually something that you guys there's actually formulas for calculating out, but that's something for the physics nerds to go and do. Anyways, but no, what this formula says here is that after 2 seconds, this object will be traveling at a velocity. If we took a snapshot and nothing else changed at that moment, after 2 seconds, it will be traveling at a rate of negative 64 feet per second. Okay? Yay! All right, let's go to our next slide here. Alright, we have some practice problems here. So at time t is equal to 0, diver jumps from a platform, diving board that is 32 feet above the water. The position of the diver is given by this, where s is measured in feet and t is measured in seconds. When does the diver hit the water? Let me grab another sheet of paper here and we can do this one really quick here. Actually, you guys can do this one. At this point, you should be able to do this on your own. So, number 1 here, this is when does the diver hit the water. So, how do I want to do this? So it helps to draw a picture for these when you're doing this. Luckily for you, your teacher knows how to use GeoGebra. So we're going to look at a picture of this. So here is a picture of the scenario that we're looking at. Let me zoom it out just a little bit here so we can look at it. Okay. So, well, that's it. That's kind of neat. I like that. So what we have here is the diver is going to start off by, let me zoom this in. This is actually kind of cool. So, come on, you can do it. Alright, so we have the diver, he comes up, he leaps into the air, and then he comes crashing back down. Gravity takes over and starts accelerating. We want to know when he's going to hit the hit the water, not the pavement. I'm sorry. So if we zoom this thing back out here really quick, okay, and he's accelerating back to the surface of the water off the diving board. We want to know at what point, at what time does he hit the water. This looks like a quadratic problem to me. So for this first one here, when does the diver hit the water? This first one is just going to be, take this quadratic and I want you to solve it for 0. So you're just finding the roots of a quadratic. What is the diver's velocity at impact? So let's take this here. We have s of t is equal to negative 16 t squared plus 16 t plus 32. So for number 1, it's just a quadratic. You're finding roots. So quadratic, find the roots. Okay, and you guys have all of your tricks from Algebra 2 and whatever we reviewed at the beginning of the year, and even from pre-calculus for finding that. Number 2 is, what is the diver's velocity at impact? So I'm going to cheat just a little bit here. I happen to know here, based upon the graph, that it's going to cross, that the diver hits the water after 2 seconds. So I know at, what is this going to be? This is at t is equal to 2 is when, is when s of t is going to be equal to 0. Okay, so this is important. So I know when t is equal to 2. I want to know what the velocity is at that point. In order to do that, I need to find s prime of t, and I just realized you guys cannot see anything that I am writing. There we go. Okay, so for number 1 here, let's go back here. So we have s of t is equal to this function. The first thing you're going to do is you're going to find the quadratic, find the roots. You guys have all your tricks for doing that. For number 2 here, we're trying to find the instantaneous velocity at the point of impact with the water, and that happens according to our graph, and it's what you should have found as well when you guys were doing the quadratic here. Remember, negative time doesn't make any sense when you're jumping off of a diving board. Okay, so we take the positive value if you ever have a negative value. So at time is equal to 2 seconds, we have impact with the water. So what we're looking for here is s prime of 2. In order to find s prime of 2, we first need s prime of t. So we're going to take the derivative of this thing. That will give us negative 32t plus 16, which means s prime of t will be equal to negative 32 times 2 plus 16. So we'll end up with negative 64 plus 16, which is equal to something, again, your math teacher cannot do in his head, negative 48. So we get negative 48 for our end value there. Alright, that'll get you guys going on this assignment. So let's take a look at the book assignment for this real quick, and then I'll end the video. Your guys' homework assignment will be page 3.5, page 117, numbers 93 through 100. So is that 8 problems for you guys to work on. Alright, so you will have time to work on that in class, and I'll answer questions at the beginning of class, and we'll see how everybody is doing. After we get through rates of change, the next section that we'll be working on will go over how to do it'll go over the quotient rule and the product rule, and leading us to our final derivative rule, which is called the chain rule, which is how we do some of our, the chain rule is kind of the equivalent of a distribution property. when we're taking derivatives. That's kind of a rough explanation, but that's the idea. Is situations where you would normally expand or take or like having to FOIL out really big polynomials, or if we would have to multiply out binomials or doing distribution or something of that nature. The chain rule kind of lets us bypass that. We have some tricks for getting around that. So yeah, that will be next class. I will see you guys in class. Let me know if you have any questions.